All right, so I'm going to start this video over. You're not aware of that, but I was recording and my battery died, so I had to start this over. So hence, you can see on the screen I already have some things written out. So go ahead and draw out your template, okay, your Cornell Note template. We are in Explore number 2, and the essential question in green we've written on our notes there. What is the law of conservation of momentum, and how can it be used to solve problems of motion? Okay, so go ahead and write down what you know or think about that. Hit pause for a moment. Okay, I'm assuming you've already written down what you know. We're breaking this apart. The Roman numeral 1, conservation of momentum. To conserve means to save. I'm conserving my money. I'm in a conservation group to save animals or the forest, right? In this case, we're talking about saving momentum, the law of conservation of momentum. Everything has momentum, right? Or inertia. You sitting at rest, you have a certain inertia, a resistance to movement. A bowling ball moving has quite a bit of momentum. It has a lot of mass, right? And so this stuff can be conserved in closed systems, as you can see, capital A. In closed systems, momentum is constant. That's assuming that no other forces act on the object, whether it's at rest or at moving. Number one, if we have two objects, object number one's momentum can be defined using the formula P equals mv. But notice we've added a few things. We're saying we're talking about two objects now. So we've got the number one everywhere, and that's signifying object one. Okay, and the I stands for the initial state. Okay, the initial state of things. Okay, so these number ones here, this refers to the first object. Okay, so don't let all that writing scare you at all, okay? Okay, and we can also say that object 2 momentum can likewise be defined with the momentum formula. It too would have an initial. In the example here, they were using the example of a hockey puck. And if I go over here, they're using pucks. They're talking about ice rinks where the surface is fairly frictionless. And so the first puck there, this is where we got that from. And the second puck, this is where we get that from. Okay, and we're writing that out right now. Okay, so we could say that the momentum of object 2 initially is the mass of object 2 times the velocity initially of object 2. Okay, and these are vector quantities. The mass is a scalar quantity. Okay, so basically what we're talking about is you got this ice rink. This is ice rink, all right? This is like a hockey, talking hockey sport. And you may have a puck. This is puck number 1. Puck number 1. And you have puck number 2. And so in this particular example, they're setting us up for these pucks to collide, as you can see. Assume that the two pucks collide with one another. Okay, so we have puck number 1 is going to come in and it's going to collide with puck number 2. Okay, so here we could assume that puck number 2 is at rest. right? This is at rest. So it has a velocity initial for object number 2 is equal to 0, right? Meters per second. And it has a mass. And over here, we could say that the velocity initial for object 1 is equal to whatever your object sets it up to be, okay? But diagrams are always helpful, okay? So kind of moving through here. After the collision, so I'm looking here at this paragraph, the first puck has velocity final, and the second puck has a velocity final, right? So once there's a collision, the puck number 2 is going to start to move, and puck number 1 may stop in its place, or maybe it'll move something, right? So let's go ahead and do this. Here we've been defining initial momentum of both objects. Now we can go and put number 2, and we can go ahead and talk about the final momentums. And for object 1, we would say that it has a momentum final. And again, we're talking object 1 is equal to the mass of object 1 times the velocity final of object 1. Okay, so we're having to break this out into its multiple parts. So here we could say that the momentum final for object 2 is equal to the mass of object 2 times the velocity final of object 2. Okay. All right. So at this point here, we may be saying, if we were to draw our diagram again, we may say that you have puck number 1 has collided with puck number 2, and now puck number 2 is going to move. This is going to have a velocity final for puck number 2 is going to equal something, and our velocity final for puck number 1 is going to equal something. Perhaps here, maybe it's going to be 0 meters per second, for example, right? It stops moving. Okay. Now, what are we trying to do here? Well, we're trying to establish a relationship. We're trying to establish this idea of the law of conservation of momentum that states that the total momentum before the collision is equal to the total momentum after the collision. Okay? So if we were to come down here and let's just make this number 3, the law of conservation of momentum. It says that the momentum, the total momentum before is going to be equal to the total momentum after. Okay. And so we could say that simply as the momentum initial of the system is going to be equal to the momentum of the system after the collision. Now, in this particular example, you had 2 objects, so we could break this up into its components. We could say that the momentum initially of object 1 plus the momentum initially of object 2 is equal to the momentum final of object 1 plus the momentum final of object 2. Okay. Now we could break that up even further. As you recall, momentum is the mass of object 1 times the velocity initial of object 1 plus object 2, the mass of object 2 times the velocity initial of object 2, and this would be equal to the mass of object 1 times the velocity initial, but not initial, final, right, of object 1, plus the object 2, the velocity final of object 2. Okay, so you could be given, you could solve, here's the key. Remember, we've been talking about algebra. You can solve for any given missing variable if the other values, right, the other variables are provided to you. And that's pretty much it. That's what this whole thing was about. And they're just going to work through videos and they're going to give you some example problems. All right. And then you're going to have some homework questions. So, what I want you to do now is I want you to write down a summary paragraph. And that does it for us. All right, you guys, take care. Talk to you soon.